Hello everyone. In this lecture, we are going to learn about solving some simple composite problems involving UV, IR and 1H NMR, and hence I am calling this as level 1 problems. Whereas level 2 problems involve UV, IR, 1H NMR along with C13 NMR and mass. They'll be called as complete composite problems, but for the time being, as far as level 1 is concerned, we shall mainly deal with UV, IR and 1H NMR. That means these are the problems which will involve the data from UV, IR and 1H NMR. By having these three data, we have to arrive at the structure of the compound. By using just UV, it is not possible to detect the structure, or by using just IR, it is not possible to detect the structure of the compound, nor by using 1H NMR. When you club these three, you can definitely arrive at the structure of the compound. We shall see how it can be done. Before going into the problem, let me just brush up your memory by explaining what information can be obtained by using UV visible spectroscopy. By using UV visible spectroscopy, one can arrive at the information about the conjugation or aromaticity present in the sample along with the carbonyl group. Whereas IR values, it will be telling about the important functional groups present in the compound, whereas it is stretching, bending, and CH stretching, CH bending, alcohol, or amide, or carbonyl functional groups can be easily detected by using IR spectroscopic information. Whereas 1H NMR spectroscopy, it tells us about the different types of protons that are present in the compound, and the environment in which they are present can be easily spoken here. As far as IR functional groups are present, you can see here, if it is an ether function, then you will be having a peak around 1075 centimeter inverse. Centimeter inverse refers to wave number ester. If the peak is around 1740 centimeter inverse, carbonyl function 1715 to 1730 centimeter inverse. If it is aldehydic, then there will be a peak at 1670 centimeter inverse. You can see here that ester will always have the highest among the carbonyl. Ester will have the highest wave number, followed by carbonyl, followed by aldehydic. The next intermediate is the anhydride, or you can say it comes as the highest in the carbonyl function, 1760 centimeter inverse. If it is acetylenic, that is C triple bond C, then it will be having around 2250 centimeter inverse. If there is aromatic CH stretching or aromatic proton, then it will be around 3050 centimeter inverse. And if it is alcoholic group, then you will have a peak around 3330 centimeter inverse. These values need not be always at the same value as it is shown here. The values may vary. Say for example, if it is ether, instead of 1075, you may get the peak at 1070 or 1080. Say plus or minus 5 centimeter inverse, it will always have as the discrepancy. So you don't have to remember the exact values, just remember the approximate values as we have seen in the 1H NMR. So once we know this information, we can now easily go into the problems. The first problem, an organic compound of the molecular formula C4H8O showed the following spectral data. He is telling he has an organic compound. It has got the molecular formula C4H8O, and he has given UV, IR and 1H NMR information. We will see what UV is telling. UV, it is showing a lambda max peak at 274 nanometer or epsilon value at 17. IR, there is a value or peak around 1715 centimeter inverse. 1H NMR, we have got three delta values. Delta 1.07, T refers to triplet, 18 squares. Delta 2.12, singlet, 17.6 squares. Delta 2.48, quartet, 12 squares. Having these data, we have to deduce the structure of the organic compound. Before going into the solution, we will see what information at the first site can be obtained from this. The very first thing that you have to understand or you have to start is looking at the molecular formula. This molecular formula C4H8O tells us that there cannot be any aromatic system. If at all there is any aromatic system, the minimum number should be either 5 or 6. Because there are only 4 carbons, this should be definitely an aliphatic compound, and there is one oxygen. and there are 8 protons. We will see what UV is telling. 274 nanometer, it is telling that there cannot be any conjugation or there cannot be any aromatic system. IR 1715 centimeter inverse, it is indicating that there could be a carbonyl group because the molecular formula also tells that there is O and there is C, so C double bond O, there could be, we are not so sure, it is not confirmatory, it is just at the first sight we can assume that there could be a carbonyl group at 1715 centimeter inverse. Coming to 1H NMR, delta 1.07, he is telling triplet and 18 squares. Here usually what we do is we give number of protons, triplet 2H, singlet 3H, quartet 2H, something like that. But instead of giving the protons, one may ask that there will be this many number of squares, convert these squares into protons. We will see how we can do that. This is the solution part. UV, as I said, it indicates the absence of aromatic system. IR, it indicates the stretching frequency of carbonyl group. Now, whenever the molecular formula is given, we know that whenever the composite problem is given, we have to understand or you have to bear in mind that you have to calculate the double bond equivalence. So to calculate the double bond equivalent, the formula is CaHbNcOD. It is also called relative abundance. The formula is A plus 1 plus C minus B by 2. So substitute here C4H8O. C is 4, 4 plus 1 plus, we don't have nitrogen, so 0 minus B is 8, 8 by 2. 5 minus 4, 1 indicates the presence of 1 unsaturation. We have here assumed that carbonyl group is there, carbonyl is C double bond O, so this double bond there is an unsaturation, and the Ra double bond equivalent is also showing that there is one unsaturation. Now the next step in this problem is we have to convert the squares into number of protons. It is very simple, it is just a simple mathematics. What we have to do is among the least squares, say for example 18, 17.6 and 12, among these the least square is 12, so divide everything by 12. 18 by 12, 17.6 by 12, 12 by 12, that is what we have done. 8 by 12, 17.6 by 12, 12 by 12, so 1.5, 1.5 and 1 we are going to get. There cannot be 1.5 proton in a compound, there should be either 1 or 2, so you have to convert this fraction into a whole number starting from the number 1. So 1.5 into 1 is 1.5. It cannot be possible. So change the number to 2. The next number after 1 is 2. So 1.5 into 2 is 3. 1.5 into 2 is 3. 1 into 2 is 2. So there are totally 3 plus 3, 6. 6 plus 2, 8 protons. See here the molecular formula is also telling that the compound has 8 protons. This is how you have to convert squares into number of protons. So here what happens? Now it is instead of 18 square, you can put it as 3H, 3H, 2H. So 3 plus 3, 6, 6 plus 2, 8. So there will be totally 8 protons. Now coming to PMR value. So PMR value, delta 1.3, sorry, delta 1.07 triplet 3H. So triplet 3H indicates that there should be a neighboring CH2 group along with this. That is what is given here. PMR delta 2.12 singlet 3H. It clearly indicates the presence of COCH3. Singlet indicates that there should not be any neighboring protons. So CH3. So CH, it is, if it is primary alkyl, then it should be 1, because the methyl is attached to some electron withdrawing substituent, then it should be a methyl ketone, and hence the value is somewhat higher, that is 2.12. Next is delta 2.48 quartet 3H. It clearly indicates that CH2 group is having one CH3 as neighbor attached to the electronegative group. This 2.48 along with this 1.07 triplet quartet, as I was told that it is the characteristic feature of ethyl group. So CH3, CH2. Therefore, the structure can be CH3, CH2, CO, CH3. Now we have to fit in the given NMR data into this compound. So this 1.7 is a triplet, and CH2 is a quartet, and it is having value of 2.48. See, triplet quartet is a characteristic feature of ethyl group. Then followed by a methyl ketone CO, CH3. The CH3 is appearing as a singlet at delta value 2.12. This is how you have to arrive at the structure of the compound. We will move to the next problem. Derive the structure of the compound that shows the following spectral data. Molecular formula is C12H14O4. Now immediately you can see that there are more number of carbons, so there could be an aromatic system, and UV is also telling that the lambda max is 280 nanometer. Definitely there is a conjugation in this molecule. IR, there are two values, 1730 and 3050 centimeter inverse. 1730, definitely it should be a carbonyl group. 3050, it is definitely aromatic CH stretching. Next is 1H NMR. He is telling delta 7.4, delta 4.4, and delta 1.5, singlet, quartet, triplet. So triplet, quartet, and this is singlet. Again, they have given in squares, so we have to convert that squares into number of protons. So once we derive the structure, we have to assign all the data to the respective group. Let us see by looking at the solution. UV, it indicates the presence of aromatic system, and IR 1730, it indicates the stretching frequency of carbonyl. 3050, it indicates the aromatic CH stretching. First, we shall find out the double bond equivalence. We will see how many number of unsaturations are there. C12, H14O4. So substitute here C12, 12 plus 1, N we don't have, so 0, B is 14. So 13 minus 7 is 6. So there are totally 6 unsaturations. Among the 6 unsaturations, 4 will be going to the benzene ring, because a ring is also considered as one unsaturation. Benzene ring will have 3 bonds. So 3 plus 1 ring is 4. 4 unsaturations is gone, and we have to now assign 2 more unsaturations. We shall see at the later stage. Now coming to converting the squares into number of protons. Here in this case, the least square is 7.1. Divide all these values by 7.1. This is how we have 7.1 by 7.1, 7.2 by 7.1, 10.8 by 7.1. So 1, 1, 1.5. There cannot be 1.5 proton, and we have to match that. There are totally 14 protons in this compound. So start multiplying by 1. 1 into 1, 1, 1 into 1, 1, 1.5 into 1. So total it becomes 3.5 proton. It is not matching. Multiply by 2. It will not. Multiply by 3. It will not. When you multiply by 4, definitely it will match. 4 plus 4, 8. 8 plus 6 is 14. So the molecular formula, it fits in perfectly into this 4H, 4H, 6H. Now he has given 3 different types of protons here. We will see 7.4. 7.4, it refers to aromatic proton. Aromatic proton, there are 4H. It indicates the presence of disubstituted benzene ring. If it is singlet 5H, then it is monosubstituted. If it is singlet 4H at delta 7.4, then it should be a definitely disubstituted benzene ring. And also you have to remember that if it is disubstituted, can we have symmetrical or unsymmetrical substitution? Definitely it should be symmetrical substitution, because he has given it as singlet. If this would have been M, that is multiplied, then you would have thought that it is a disubstituted benzene but unsymmetrically substituted. Because he has given it as singlet, then it should be a symmetrical substitution. Now delta 4.4 and 1.5, triplet and quartet, it indicates the presence of ethyl type group. So therefore the structure is, first write the benzene ring, then 2 substitutions, so it becomes disubstituted. What can you have? And also you have to remember that there are 4 oxygen in this molecule. 4 oxygen, it refers to ester type, COO. We have told that there is a carbonyl stretching, so CO, because it is 173, if it would have been 1715 or 1720, it is just a carbonyl. That means it is a ketone. Since it is 1730, it should be definitely an ester. So COO, CH2, CH3. Where this CH2, CH3 is coming from? Because it is triplet quartet. It is a characteristic feature of an ethyl group. Whatever you write on the top, the same thing has to be written on the bottom because it is a symmetric molecule. Now we will see. So 7.4, here two protons are there, here two protons are there, and because it is singlet, because of that we have written it as a symmetrical substitution. 4.4, so definitely this is 4.6 or 4.4 because the value is higher since it is attached to electronegative element oxygen and also the anisotropic effect of the carbonyl function, and this is CH3 primary alkyl. The value is quite high because it will have the influence of electronegative effect as well as the anisotropic effect of the carbonyl function. So this is the structure of the compound for the problem 2. We will move to the third problem. An organic compound with molecular formula C6H10O4 showed the following data. UV, no significant absorption above 210 nanometer. It indicates that the aromaticity or conjugation is completely absent in this molecule. IR 1760 centimeter inverse, and it is showing a very strong value. You have to remember that 1760, it cannot be ketone, maybe ester, or maybe anhydride also. PMR, there are three different types of protons: 1.3 doublet 3H, 2 singlet CH, 6H, 6.8 quartet 1H. So there are three types of protons. Here you don't have to convert it into H, because there are no squares given. It has directly given the number of protons. 6 plus 3 is 9, 9 plus 1 is 10. So H10, it is matching with the PMR. Having all this data, we have to deduce the structure of the organic compound. We will see how we can substitute. So UV, it indicates the absence of conjugation and aromatic ring. 1760, it indicates the presence of anhydride or ester. We will see what it is. And we have to calculate, the first thing is to find out the double bond equivalence. So substitute C6H10O4 in this formula. C6, nitrogen is absent, so hydrogen is 10. So 7 minus 5, 2. It indicates the presence of two unsaturations. Now we will come to the PMR data. The first one is 2, delta 2 is telling singlet 6H. So 6H singlet refers to, there are two methyl groups, CH3, CH3, but it cannot be just CH3 because the value should have been only 1, because the value is somewhat higher. Then definitely that CH3, the two CH3 groups, they are different and they are attached to some electronegative element. We will see what it is. 1.3 doublet 3H. So indicates the presence of 3H refers to another methyl group, but it should be attached to CH because it is showing doublet. Another one, delta 6.8 quartet 1H. It indicates the presence of CH with adjacent CH3 group. So these two must be adjacent or neighbor to each other. So what the structure can be, there are two COCH3 groups. There is one CH3 group attached to CH. There is one CH attached to CH3. So what we can write, CH, CH3, CH3, CH3. But the molecular formula, it is telling that there are 4 oxygens. How to match the 4 oxygens? Now they are telling that from the IR, it is either anhydride or ester type. So now substitute COO on either side of the CH, to which the CH3 is attached, and the CH3 is definitely attached to CO, and hence the value is somewhat higher, that is delta 2. That's why the structure is this. This is the anhydride type of molecule. CH3CH, OCO, CH3, bottom also OCO, CH3. Now we have to assign the NMR values for this. So 1.3, it is doublet because the neighboring proton, there is only one H, and hence it is appearing as a doublet, and this is appearing as quartet because the neighboring is, there are 3 proton, 3 plus 1, n plus 1 rule, that is 4, that's why it is showing quartet. It is having very high value, 6.8. It is like your tertiary alkyl group. Definitely it is tertiary alkyl, so it should be 1.3 or 1.4, but the value is quite high, that is 6.8, because this CH is attached to 2 oxygens and 2 carbonyl groups. there will be more electronegative effect of oxygen and more anisotropic effect of the carbonyl function, and hence the structure can be written like this. So the CH3, that is methyl ketone, it is appearing at delta 2 as a singlet because there is no neighbor in this CH3. Coming to problem number 4, deduce the structure of an organic compound with the following data. Molecular formula is C8H6. It clearly indicates that there could be an aromatic system. IR 2250 centimeter inverse, 1600 centimeter inverse. 2250, as I've already told in the beginning itself, it is the characteristic feature of the acetylenic group. Then the PMR is telling that there are only two types of protons. One is 7.4 multiplied 5H. This is the characteristic feature of monosubstituted benzene. 3.0 singlet 1H. We will see what it is. So IR 2250, it indicates the presence of acetylenic group. And now we shall find out the double bond equivalence CaHb and COD. For the molecular formula C8H6, substitute 8 here and 6 here. 9 minus 3 is 6. It indicates the presence of 6 unsaturation. 6 unsaturation refers to there should be one benzene ring. For benzene ring, there will be 4. 3 double bonds and 1 ring. So 3 plus 1 is 4. We have to check what 2 unsaturations are remaining. Coming to PMR, 7.4 multiplied 5H, it indicates the presence of monosubstituted benzene ring, and 3.08 singlet 1H, it indicates the presence of CH acetylenic group. So the structure can be written as benzene ring, C triple bond C, CH. So this is monosubstituted benzene ring, 7.4 multiplied can be written here. Only 1 H for the acetylenic, and hence it is singlet. There is no neighbor for this. So the value is appearing around 3.08. Coming to fifth compound. Deduce the structure of the organic compound. Molecular formula is C5H10O2. So it cannot be an aromatic system, or there is no conjugation. 1740, it indicates that there could be an ester. PMR 1.3 doublet 6H. He has given coupling constant here, J is equal to 8 Hertz. Delta 2.4 substrate 1H. J is equal to 8 Hertz. Delta 3.6 singlet 3H. So J is equal to 8 Hertz, J is equal to 8 Hertz. It refers that these two protons are nearby each other. These two protons are neighbors to each other, and hence the J value is same. We will see what the structure is now. So IR, it indicates the presence of ester functional group. So the double bond equivalence, it is coming to 1. That means there is only one unsaturation in the compound. PMR 1.3 doublet 6H. So doublet septet, I've already told that it is the characteristic feature of isopropyl type. It indicates the presence of isopropyl group. 2.4 substrate indicates the presence of CH attached to 2 CH3 groups. So these two, they are neighbors to each other since they have got same coupling constant. So this is CH, CH3, CH3. And 3.6 singlet 3H, it indicates the presence of methyl ketone. So on one side you write the isopropyl group, on the other side you write CH3, but the molecular formula is telling that there are 2 oxygen. So satisfy it by attaching an ester COO attached in the middle. Therefore the structure is found to be this one. So this is a singlet, this is multiplet, and this is doublet. Instead of substrate, we can write it as multiplet also. The next problem, deduce the structure of the organic compound that fits the following data. UV 260, and it is telling it is a very weak peak. IR 1715, carbonyl stretching frequency. PMR delta 2.1 singlet 3H, delta 3.7 singlet 2H, 7.25 multiplied 5H. So this indicates the presence of monosubstituted benzene ring, and there are 2 different types of protons. One is CH3, another one is CH2. They both are not neighbors because they are appearing as singlet. If they would have been neighbors, then it would have been triplet and quartet. Since it is singlet and singlet, they should be separated by some other entity. we will see what it is. So IR, it indicates the presence of carbonyl or ketone group. 2.1 singlet 3H, it should be definitely a methyl ketone. And 3.72H, it indicates that CH2 is attached to CO, and CH2 and CH3 are separated by CO because it is singlet. 7.25 is the monosubstituted benzene ring. So write first monosubstituted benzene ring, then CH2 here, CH3 here. In the middle, you have to put it a carbonyl group, C double bond O. The next compound, an organic compound with molecular formula C9H10O2. It indicates that there is a benzene ring. It has a strong band in the IR spectrum at 1690 centimeter inverse. We will see what it is. It should be an carbonyl group, but we have to check whether it is ketone or aldehyde. Its PMR spectrum showed following signals. Identify the compound and interpret the spectral data. 2.5 singlet 3H, 3.9 singlet 3H, 7 doublet 2H, J is equal to 12 Hertz, 8.1 doublet 2H, J is equal to 12 Hertz. That means the 7 and 8.1, these two protons are neighbors to each other since the coupling constant is same for them, that is J is equal to 12 Hertz. But you must see here that it should be a disubstituted benzene ring, but in this case it is not symmetrically substituted, it is unsymmetrical substitution because one is giving 7, another one is giving 8.1. As I said, IR, it should be a carbonyl group. We don't know whether it is aldehyde or ketone. We shall check up later. Calculate the relative abundance or double bond equivalence. It comes out to be 5. So 5 indicates the presence of a benzene ring. So benzene ring, we will have 3 plus 1, that is 4. One more we have to check what it is. Then PMR, singlet 3H at delta 2.5 indicates the presence of methoxy group, that is ether function. There are 2 oxygen, so we have to satisfy one for carbonyl group here, another for methoxy group. Next is delta 3.9 singlet 3H. It indicates the presence of methyl ketone, but it is attached to aromatic system. Methyl ketone is usually 2.1 to 2.4, but the value is quite high because the ketone is attached to the aromatic system. Next, delta 7 doublet 2H, J is equal to 12 Hertz, indicate the presence of aromatic proton. Delta 8.1 also indicates the presence of aromatic proton. So these 4 aromatic protons indicate the presence of unsymmetrically disubstituted benzene. If it was symmetrical, then it should have been singlet singlet. Because it is unsymmetrically substituted, it is having different multiplicity. So therefore, write benzene and 2 substitutions here. On one side you write methoxy group, on the other side you write methyl ketone. So now assign all the values. Benzene, this side is 7, this side is 8.1. One may ask why it is so. This methoxy is electron releasing group and hence it is showing more shielded. So hence the delta value will be less. Whereas on this side it is carbonyl group, we will have both anisotropy as well as electronegativity, and hence the value of this proton is quite high compared to this proton. This proton is coming more de-shielded, whereas this is quite shielded compared to this proton. Then the next one is singlet at 3.9 refers to methyl ketone. 8th problem, reduce the structure of an organic compound with the following spectral data. Molecular formula C10H12O2 UV220. We will see whether there is any aromatic or not. IR, there are 3 values, 3077V, 1745, 1608. For the first instance, we know that there is a carbonyl group. 7.3 singlet 5H, it indicates the presence of monosubstituted benzene ring. 5 singlet 2H, 4.2 quartet 2H, 1.2 triplet 3H, 2H 3H, quartet triplet, it indicates the presence of ethyl. So 3077 is for aromatic CH stretching, 1745 is for carbonyl group. We will see this at the later stage, 1608. So the relative abundance comes to be 5. So 5 includes a benzene ring for which 4 is gone. We have to check one more. And coming to PMR, so it is a monosubstituted benzene ring, right? Monosubstituted benzene ring here, 1.2 triplet 3H. So it indicates the presence of a methyl group attached to CH2, 4.2 quartet 2H, it indicates the presence of CH2 attached to a methyl group, but the value is quite high for CH2. It should be usually 1.3 or 1.5, but it is quite high. That means it is attached to an electron withdrawing group. Then the other one is the delta 5 at 2H, and it is quartet. Sorry, this should have been a singlet, not 2. This is singlet. It indicates the presence of CH2 attached to more electron withdrawing groups. Because the value is high, it shows that more electron withdrawing groups are there. So first, based on this, you have to arrive at the structure of the compound. First, write the monosubstituted benzene ring. Then there is a CH2 group. There is ethyl group, CH2, CH3. But the molecular formula tells that there are 2 oxygen atoms. So one is carbonyl. We know that it is from 1745. And this CH2 is attached to one oxygen. That oxygen is in turn attached to the benzene ring. So this is monosubstituted singlet 7.3, CH2 singlet 5, CH2 quartet 4.2, CH3 triplet 1. Next problem is, this is the kind of problem which involves a chemical reaction, and you have to predict the structure based on the NMR data as well as the chemical reaction. He is telling that there is a compound called 4-pentanoic acid. Upon treatment with dilute H2SO4 gives a lactone. So 4-pentanoic acid, when you treat that in presence of H2SO4 in diluted condition, it gives a lactone. That lactone has presented the following NMR data, and we have to assign the structure and explain the data. So what the data he has given is delta 1 doublet 3H, delta 1.3 quartet 2H, delta 2.5 triplet 2H, and delta 5 sextet 1H. So this is the reaction. We have to first write the reaction and we have to complete and predict the product. This is pentanoic acid. Pent means 5 carbon, 1, 2, 3, 4, 5 carbon. Acid, COOH, that is the functional group for carboxylic acid. 4-penti. So at fourth position, 1, 2, 3, 4. At fourth position, you are supposed to put a double bond. So this is the structure of 4-pentanoic acid. When it is treated with dilute H2SO4, it undergoes a cyclization reaction to form a lactone. What are lactones? They are the cyclic esters. Cyclic esters are called lactones. So this is the structure of the product for this chemical reaction, and he has given the data for this. Now for this data we have to check. He has not given the product. You have to predict the product and then assign the data. So the product may be this. Now we have to assign the structure and we have to check what is what. The first one is delta 1 doublet 3H. So doublet 3H means there should be a methyl group, but that methyl group is attached to another CH because it is giving a doublet. The neighbor should have 1. 1 plus 1 is 2, that is doublet. Next is 1.3 quartet 2H. 2H indicates the presence of CH2, but the neighbor should be CH3, or in this case it may be different. Next is delta 2.5 triplet 2H. 2H indicates the presence of CH2 with neighboring another CH2 because it is a triplet. The last is delta 5 sextet 1H. It indicates the presence of CH, whereas the neighboring it should be having more number of hydrogens. That is, it should be 5. That is CH3, CH2, 5. 5 plus 1 is 6. That's why it is sextet. Now we will see whether this is the correct structure or not. First is 1 doublet 3H. So there is CH3 and the value should be 1, and it is an ordinary primary alkyl group, and the neighbor is CH here, and hence it is showing doublet. Next is triplet delta 2.5. Why it is triplet? Because the neighboring should be 2. 2 plus 1 is 3, and hence it is triplet. Then this is also delta 1.3, and it is CH2, but it is quartet. Why it is quartet? Because here it is doublet, and there is one more proton here. So 2 plus 1 is 3. 3 plus 1 is 4. That is this club together 3, and this is 1. 3 plus 1 is 4, and hence it is quartet at delta 1.3. The remaining is 5. This is CH. There is only one proton, and the multiplicity is sextet. So for this, one neighbor is CH3, another neighbor is CH2. That is 5 plus 1 is 6, and hence it is sextet. This is the kind of problem that you can usually expect in competitive examinations or ordinary examination that happens in colleges or universities. The next problem, two isomeric compounds. So this is isomer based compound or problem. So the molecular formula of the isomers is C4H8O3. So there are two structures possible for this. So these two isomeric compounds with this molecular formula give the 1H NMR spectral data, and you have to deduce the plausible structures for them. Isomer 1, it is showing delta 3.5, 3H singlet, 3.8, 3H singlet, 4.95, 2H singlet. So there are three oxygen, you must remember in mind. So there should be an ester or a carbonyl function, and also I'm expecting that there could be an ether function for this isomer 1. Why I'm suspecting? 3.5 singlet 3H. Singlet 3H refers to CH3, delta value is more, and hence it should be an ether type function or methoxy type. Another one 3.8 3H singlet. So definitely this should be attached to some ester function type or ether function type. We will see where we can attach 3.5 and 3.8. 4.95 2H singlet. So all the three protons are not having any kind of neighbors, and hence it is showing singlet, singlet, singlet. It is CH2, this is CH2, this is CH3, and this is CH3. And we have to also satisfy by bearing in mind that there are three oxygen atoms in the molecule. So one is singlet CH3, CH2, CH3. In between, you have to play with the number of oxygen atoms. Between these two, you can put an ester function. Between these two, you can put an ether function. Why you have to put a function here? Because it is showing 3.5, and this is for the methyl ketone. Why methyl ketone is somewhat as 2.3, 2.5, but it is more because there is another oxygen atom. That's why I'm putting more here. And this is the ether function. Ether function is usually 3.5 to 3.8. That's why for this side you have to put O, and for this side you have to put ester function. So this structure perfectly fits into this data given. The next isomer, he is telling there are 1, 2, 3, 4 different types of protons, but having the same molecular formula, different structures. That's why they are called structural isomers. Delta 1.3 3H triplet J is equal to 7 Hertz, 3.6 2H quartet J is equal to 7 Hertz, 4.15 2H singlet, 12.2 1H singlet. By looking at this value, you can arrive at two conclusions now. The first one is these two protons are nearby each other because they have got the same coupling constant value of 7 Hertz, and that is the first clue that you can obtain. The next clue is 12.2. The highest possible chemical shift for a proton that can be given is for the carboxylic acid, that is 1H singlet. So there is carboxylic acid. Another one shows that these two are neighbors to each other, and also you can see that triplet quartet 2H 3H, it indicates the presence of ethyl type. So three protons we have worked out. One is ethyl function, another one is carboxylic acid function. So you can easily write CH3 CH2 one side, carboxylic acid on the other side. Also you have to bear in mind that there is one more oxygen, 2 oxygen we have put for carboxylic acid, one more oxygen we have to put. So definitely it should be for the ether function. So another one is 4.15 2H singlet. 2H refers to CH2. You have to put CH2 here, and all the 1, 2, these two are singlet. That means these two are not having any neighbors, whereas these two triplet quartet, they are neighbors. Also another way of putting the unsaturation is by calculating the double bond equivalence for this. For this double bond equivalence works out to be 1. For this double bond equivalence works out to be 2. So 2, sorry, this is also 1 because there is only one carbonyl function, and here also there is only one carbonyl function. So for both unsaturation will be 1. The next type of compound, it is not composite problem, but this type of problem is quite important for competitive exams especially. Molecular formula of a compound is C8H14. C8H14. And the hint that he has given is it contains two non-equivalent sets of protons. Write the structure. As soon as we see C8H14, the immediate thing that comes to our mind is there should be an aromatic system. But every time that is not the case. But he has given that there are two non-equivalent sets of protons. That means there are two types of protons. You must obtain two signals and you have to write what is the structure. He has not given any chemical shift value. He has not given any multiplicity. The only clue that he has given is there are two non-equivalent sets of protons. We shall see what this can be. So this kind of problems, it is all only trial and error basis. So you have to write one structure. If it does not satisfy, you have to change it to another structure. And for this, if you calculate the double bond equivalence, it comes out to be 2. So on one side, we have to write that there should be an isopropyl group CH, CH3, CH3, and it should be definitely a symmetrical molecule because he's telling that it contains only two non-equivalent sets of protons. If it was more, then it cannot be any symmetrical molecule because he has given only two non-equivalent sets of protons, and definitely there should be a symmetry in the molecule. So on one side you write the isopropyl group, on the other side you write the isopropyl group. Because isopropyl group, it refers and to have more number of protons, 3 plus 3 6 plus 1 7. So on one side you will have 7 protons, on the other side also you will have 7 protons. So 7 plus 7 is 14. So this CH is different, this CH3 is different. So two sets of non-equivalent protons, it is satisfied. Protons 14, it is satisfied, but we have to check the number of carbon atoms also. So here 1 2 3 1 2 3 3 protons we have taken. 3 plus 3 is 6. We are left with two more protons. Two more protons, two more carbons. You write it in the middle, C C, and you have to satisfy it by putting the double bond or triple bond or single bond. For this compound, you have to write the triple bond. So when you write this triple bond, so this is a kind of substituted, symmetrically substituted alkyne structure. And this, for this formula, molecular formula, this is the best possible structure that we can assign. Similarly, another kind of problem, C9H18O shows a single sharp peak at delta 1.3. Write its structure. C9H18O. As soon as we see this compound, immediately we say that there could be an aromatic system. So in order to rule out whether there is an aromatic or not, you have to check the double bond equivalence. If you calculate double bond equivalence for this compound, it comes out to be only 1. So it clearly indicates that aromatic system is absent, because aromatic system minimum it should have 4. 3 double bonds, 1 benzene ring. So 3 plus 1 is 4 unsaturation. Because it is showing 1 saturation in this compound, definitely the aromatic system is completely absent. And it is telling that it shows a single sharp peak at delta 1.3. 1.3 refers to usually methyl primary or methylene secondary. We can check it by trial and error. So if you put, there is only one oxygen, if you put oxygen and in the middle, and if you think that it is a symmetrical molecule and ether type, so you have to satisfy it by putting isopropyl. Isopropyl, we will have 3 carbons and 7 hydrogens. 7 plus 7 is 14, but here there are 18 protons. Now you divide 18 by 2 because the molecule, it appears to be symmetrical. If you divide 18 by 2, then you will have 9 protons. 9 protons refers to 3 methyl groups, CH3, CH3, CH3. Which group can have 3 methyl groups? Definitely it is tertiary butyl. So on one side you put tertiary butyl, on another side you put tertiary butyl. So we are done with 1, 2, 3, 4 carbons. 4 plus 4, 8 carbons. 8 carbons and 3, 3, 3, 9, 3, 3, 3, 9. 9 plus 9 is 18. C8, H18 we have done. But we are left with 1 C and 1 O. We know that there is only one unsaturation, and hence it should be C double bond O. Put C double bond O in the middle, one tertiary butyl on LHS, another tertiary butyl on the RHS. So this is how you have to predict the structure by trial and error method. And this is self-study problem. You can take screenshot of this and try to solve by yourself. If at all you have got any doubt, please let me know in the comment box in the YouTube channel. Problem 13, identify the structure of the organic compound from the given data. Molecular formula is this, 1H-NMR is this. Again, I'm telling you, this is not composite problem. It is just for the practice purpose based on only NH-NMR data. So there is a nitrogen in this molecule. So be careful while calculating the relative abundance or double bond equivalence. You have to include for C also, CHBNC, OD. There is no O, instead of O, there is one N. Another function, he is giving a clue that there is an amide functional group in this molecule. He has given 1H-NMR data along with the molecular formula. You have to arrive at the structure. For this compound, he has given molecular formula and 1H-NMR data. You have to arrive at the structure. The last problem is predict and interpret the 1H-NMR spectra of 2-chloropropanoic acid and 1-nitropropane. So in the last lecture, I have already shown how to write the spectrum of ethyl bromide, or sorry, propyl bromide. Based on that, you have to write the 1H-NMR spectrum for these two compounds. So this is 2-chloropropanoic acid. Prop, the base is, it has 3 carbon atoms. Among the 3, one will have acid group, functional group, COOH, and for the second position, and you attach 2-chloro and write the 1H-NMR spectrum. 1-nitropropane, it is very simple. Write propane, 3 carbon atoms. At first carbon, you put a nitro. So why we are giving these practice problems is because when the functional group, the neighbor, the electronegativity changes, the spectrum also changes. So you just have a practice of this. If at all there is any doubt, please come back to me on the YouTube channel. Thank you very much.